Hi guys, how's it going? So today actually we're gonna be going through a machine learning system design concept. We're gonna be designing a system that can be able to detect if a listing on an e-commerce platform is illegal or not. I thought this problem was quite interesting looking at companies like Amazon whereby they have like over 6 million of vendors. So how do we build a system that can scale at that number of vendors while we still make sure that we maintain a low latency and high throughput? So it's going to be an interesting one. Without wasting any time, let's see what the things that we're going to cover. So we know that the people who are going to be uploading the listing on the site are going to be the vendors, right? However, there are some vendors who are going to explicitly be able to upload those legal listings. So this could be through a description or the image of the posting, right? However, there are some who are going to upload a legal product, but implicitly so. So by that, I mean like someone could be selling a TV, but inside that TV, it could be a 6 kg of meth. So my assumption is that we need to be able to detect both people who upload illegal listing explicitly and implicitly so, right? So we will see how we can go about that. My second question will be how many data do we have? Given the scale of the company, I think we have millions of listings looking at the historical data. So, however, it could be that we don't have like enough listings, illegal listing, so we have some sort of like imbalanced data. So I think we might be having something like 0.05% of like illegal listing. So it's going to be quite challenging. So we need to find a way in which we can still achieve a good model given the small number of illegal listings. The second question that I'm going to ask is that do we have some sort of like a label data? The data could be labeled, but for the most part, the label data is not enough, especially given like if you want to capture like very complex interactions. So we're gonna need more data. So we're gonna take about how we can easily label more data, right? From a production standpoint, I would like to understand if like we want to detect the legal listing as the user or the vendor upload, or do we want to like detect them like maybe after like maybe few days or so. So can be achieved two times. So the reason I'm asking this is because it's going to influence how we design our MLOPS system. So we will see how we're gonna cater for this question also when we get there. The the fourth thing is that is model explainability. So this requirement can be debatable because you don't want to detect people, then you want to tell them how you caught them, right? They will know, then they will use different techniques. So I'll say like also this one is debatable. I wouldn't say I will go hard on like having model explain to explain why some of the vendors were 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 caught or something like that, right? Um, with regarding to the type of machine learning problem that we're solving, is this going to be a supervised or unsupervised? So I think let's go into the trade-offs of the system and we will see which one based on the trade-offs is the one that we can go with. For now, I think let's put this requirement on hold. Then we'll come back to it as we continue. In addition to the functional requirement, we're going to have like non-functional requirement whereby we are required to build a low latency system and we need to minimize the training time. We need to automate the training, evaluation, and deployment processes. So we'll see how when we get there. So I'm gonna start with the data scientist playground. So you can think I'm calling it playground because I see this as a point whereby we're trying to experiment. So this will consist of like collecting the data, we processing it, we modeling, we evaluate. So our source could be that we have some sort of like an S3 whereby we store the images of the listings. We have a data warehouse whereby we store the vendor profile. We could be storing product description and text document into MongoDB. So what we want to do is that we want to consolidate all of these data sources to create, to profile a vendor and also to create a data set for our project. So how do we then identify and label the data? This could be quite hard. One way we can do this is that users usually on Amazon, you can report abuse. So we're gonna leverage the listings that have been reported and see if maybe this report has to do with like a listing having some sort of like it was a legal listing or a gun. That could be our start to collect the data that is more or less labeled. We can leverage advanced labeling techniques. One labeling is that we can do a hands labeling. So this is like we assign a group of experts or humans to label the data manually. However, this is painfully slow, and this is because given like how many listings we have, it will take them so much time. The disadvantage of also hand labeling is that we can find that people can not agree which listing is a card or not, right? We'll see when we get there. We can leverage weak labeling, so we can leverage things like heuristics. For example, we can write like functions whereby we try to detect if a listing contains a card or not. And we can write these labels in a form of functions. Then we can take our data set and run them through these functions. And by the end, we should be having a solid label data set. So for instance, if we take this listing here, we can see that it states that stun gun. However, the image here does not show any gun, right? Like it's still a stun gun, but it does not show any gun. So it depends also how we trained our model. Another technique that we can leverage is called transfer learning in zero-shot model. So the zero-shot model is like using models such as GPT to label your data. However, this is quite expensive given the limited resource that we have and given the number of listings that we need to label. We can be spending a lot of money on this. So I think we can write that one off. Given all of these techniques for labeling data, I think what we can do to come up with a good labeling is that we can leverage active learning. So with active learning, you can think of like we try to have human intervention, right? We label a set of data, right, at the start. So we start having a seed. We call this a seed. So this data is labeled. Then we push this labeled data into our model. Then the model metadata is used along with unlabeled data, right? It's used along with unlabeled data. So this actually enables us to see which of the points we're still not good at. Then we train some sort of like a ranker. So this ranker here is going to rank all of these points that a human will need to relabel again. So you can think of this, it's a continuous thing that is keep on going. So we keep on making our data set as strong as possible as we're iterating through this. So active learning is quite one of the growing field in like labeling techniques or something like that. So given that, I want to talk about features. This is like one of my favorite topics because I feel like feature engineering, that's where you become creative. You kind of like think out of the box. So the first feature that I'm going to think of is the account age. My assumption here is that vendors who just recently started selling might actually be selling illegal listings, because they just started now and maybe they don't have something like that, right? We can look at reviews. My assumption is that people will probably describe how they use the product. So maybe the reviews can actually help us to actually be able to understand. we're gonna look at vendor reputation. So number of reports, how many times was the vendor reported, like, right, looking at this. So also this can be quite helpful. So now, given that, what I'm gonna do is that I'm gonna then group all of these features into like groups. So we can think of like, now we have product features or listing features, whereby we have title, description, image, category, and we can have a vendor category, which also looks at the reputation of the vendor, location, account age, something like that. We can also look at the buyers, people who are buying these products, like, their account age, how long they have joined Amazon, they created Amazon account or something like that. Can look at their IP addresses and stuff like that. Because we said that we want to cache implicit listings, whereby vendors could be hiding the illegal product, then we're gonna have to look at behavioral features. By behavioral features, these are the features whereby we essentially try to see interactions between buyers and sellers. We try to see like their age, all of this stuff. So it's not like necessarily static, like a title is static, but these are like more frequently changing features. So that we're gonna look at. For instance, I think we can look at how long does it take to sell the product. Like, let's say the vendor posted the product today. How long does it take to make sure that the product is being sold? Something along those lines. We can look into. Um, let's go to the next section. So we spoke about a lot of things. Now I want to talk about how are we then going to clean the data. So because we spoke about like things like description, we talk about things like title, we spoke about things like reviews. So we need to clean this data before we pass it through our model. So the first thing that we can do is that we can tokenize the text. So there are different type of tokenization that one can leverage. You can do a word tokenization. You can do character tokenization. A word tokenization, we can have high vocab, which can also lead to us having high embedding space. But with character level, we can have low embedding. However, we can lose the meaning. So we can leverage something like subword tokenization, whereby we use a byte pair algorithm. That's something that we can also use. We can lower our text to normalize it, and we can apply techniques such as like monetization and stemming, and we can remove stop words and Unicode characters. So now we have the text. We kind of like have it cleaned. Now we need some sort of like a numerical representation of this text. What techniques are we going to use then to get this text into a numerical form? We can definitely leverage back of weights. So we can think of back of weights like we're creating a count of weights frequency. However, the problem with back of weights is that they suffer from out of vocabulary and there is no ordering from the weights. You can think like you have like some sort of like weights, then you can't. And for instance, let's say another thing that they can suffer from is that they don't capture like the importance of weights. For example, let's say a listing, every listing product is gonna maybe say, I don't know, maybe let's say it's all about soccer stuff. No, maybe it's gonna have ball, something like that, right? And this it's gonna give too much weight to this. But then it does not make sense because this is soccer. So we are expected to talk about ball, right? So that's why we're using this technique called TF-IDF, which try to say we try to make rare weights to be important. So we use the TF, which measures the frequency of a term in the document, and the IDF measure how important a term is. However, this method also suffers from not capturing a meaning. So, for instance, a pistol and a gun, these are the same, but it will treat them as different. So, with weight-to-vec, we trying to push all the weights that are pretty much like have the same meaning into the same space, close together on the space, right? So it's where like the semantic weights are mapped close in geometrical space. That's what I mean. However, they lack some sort of like context. And I want to clarify this because some of you maybe might be confused why from a context, which context am I referring to? So I am referring to the context whereby word to vec, essentially if you give it some sort of like a gun, right? A gun could have a different meaning in different sentences. For example, a gun could refer to a muscular arm, a gun could refer to a weapon, right? So it does capture the context, but I'm saying that that word in different sentences could have different meaning, and word to vec does not capture that. That's my point, okay? So that's why now the transformer models comes into play. They try to solve this problem because they can be able to give weight to token, and they do this like on a sentence level. So if like you use a gun in a context of like weapon and you use a gun in the context of like muscular arm, they will be different. So they will be weighted differently in some way, right? So that's what I mean. But these models, as much as we continue to go to for accurate models, they come at the expense of latency. So these models can be quite expensive to run in production. So we need to find some sort of like a balance to say, okay, we still want to be accurate, but then we still want to minimize latency as possible, right? So we're gonna get into those techniques whereby we see how we can actually leverage some of the deep learning efficient method to make sure that our models are efficient. So now we spoke about using images also as like our features. So we can use transfer learning, and we can use some of the models that are already there, like EfficientNet, VGG, ResNet. And so we can fine tune our model to our use case. There are three kinds of transfer learning. So essentially, if we have a small data, we can freeze the CNN layers and replace the FS, the full connected layer for new data set. If we have a somewhat a moderate data set, what we can do is that we can keep the early layers freezed, right? While the later stage layers of the CNN are unfreezed, including the FSV, the fully connected layer. Then we fine tune those. If we have a very large data set, then we can train the CNN from scratch. So this is just like heuristics on how we can fine tune our model based on like the data that we have. And also it depends on the compute. But it has been proven that transfer learning can be quite important or increasing accuracy. So we're gonna look at sparse features, right? So we have account ID. We know that software engineers have built things such as ID generation service. So we're getting unique ID for each vendor. However, if we're gonna apply techniques such as one-hot encoding, like I said, Amazon has like 6 million of like vendors, then you can imagine how sparse these embedding are going to be. So one way we can solve this problem is that we can use this paper by Google. It's called deep hash embedding. So what it does is that it tries to apply multiple hashing of like given an ID. Then we try to create a deterministic neural network that is going to produce embeddings for us. Then we use those embeddings into our model. We can keep the model. The model might not be expensive. We can try to prune it or something like that. We're gonna get into those techniques at the later stages, but we can try to make sure that the model stays as stays as low as possible in terms of parameters. It's not expensive. But the point here is that like we having vendors every day, like, right? And so because of we have vendors every day and we need to be able to manage them. So I thought maybe this technique whereby we have a model that create embeddings and which are deterministic I thought it was a good idea because we handle a lot of things like out of vocab, um, new vendors coming in. We're handling a lot of those things. So I thought it was actually a good technique. Um, we can look at vendor age, whereby we try to do something like meaning coding based on the target. We can do things like vendor reputation, and use techniques such as decategorization, whereby we have different ones like uniform, quantile, and k-means. So we take the number of reports and we try to kind of like uh, bin them. So that's what it means. We try to bin them, and you can think of this as like different type of discretizations that we can use. So the uniform try to preserve the probability distribution, whereas the quantile try to number the observation in equal format. We can have item features and categories, so we can also embed this using some sort of like hashing tricks or something like that. If we have um, category IDs, or we can use like hashing functions such as footprint, so which are greater than hashing functions such as MD5, because these ones have high latency. And another thing is that these are more deterministic, so that's why I think we should go for fingerprint. We can use techniques such as cross features to concatenate two features to make sure that we capture like complex interaction. Also, this could reduce the number of features that we should be sending to our model. So it's a good technique. I'm not going to talk about techniques such as normalization, standardization, but these are other techniques that one should know and we can apply just to make sure that we have a very powerful model. So we know that this is going to be probably a binary classification uh, based on like how we've been designing it. So, but the problem is that even if this is a supervised, we're facing a problem of unbalanced data set because, like I said, I think probably we have like 0.5% of like illegal listing because there must be way, way, way too low, right? Compared to legal ones. So we have way, way, way too low data. So we need a way to kind of like handle this problem. So one way we can do is that we can use the downsampling and upweighting technique. So we can think of like downsampling as we reduce the majority class. Then after we reduce the majority class, we upsample it by adding the weight to the downsample class. So what I mean is that you can think of like we have 1 into 20 positive, 1 into 20. So 1 into 200, I mean, then we reduce this to 1 into 10. Then it's like we were coming from, I think this is going to be 0.5%. Then we use this factor, we multiply it here against the weight. So we multiply against the weight. Then that's how we kind of like make sure that we solve the unbalanced target label problem. So it enables us to have like the faster convergence and also optimize our disk space. We can treat logistic regression as our baseline model, right? So logistic regression guarantees us like a very fast inference time, and we can have model explainability. And the good thing about logistic is that it makes no assumption about the class distribution, right? However, the real world is not linear in a way. So the downside about logistic regression is that it does not capture like complex interaction between features. So we can probably look at another model like SGBoost, right? So SGBoost also guarantees us model explainability and is quite efficient in production. However, given the scale of like companies like Amazon, whereby products or listings are created almost like every day, it could become quite difficult to maintain SGBoost. So due to like trees becoming more deeper and deeper and deeper, I do get it that SGBoost can be quite good at heterogeneous columns like age, weight, but they do not do well in like deep learning, CV and NLP homogeneous data. So my point that I'm raising here is that you can think of like SGBoost as we have a feature like age. It's going to be able to find a way to split it in such a way that is much easier to explain, like category, like time, something like that. But with like our multi-layer perceptron, we weight the age, we weight the category to get the output. So deep learning can be able to handle like a lot of data, right? Like Amazon has like millions of listings, so we want to capture like complex interactions, and because we have more data, deep learning models can also be um, a good way to be able to solve this problem. So it can be able to handle homogeneous data. Like I said, that we have multimodal data, like we have images, text, and sparse features. You can be able to kind of like grab all of those and make a good model. So that's the advantage of this. But it can be quite expensive if it is not designed with latency in mind, and it can be quite expensive in production. So, given these models, this is the final architecture that I came up with. So I am saying that one way we can go about this is that we can have all of these features that we spoke about, and we can have their embeddings, and we concatenate all of them. Usually, some techniques it's common to use dot product. So essentially, the goal here is to capture all the signal from different features, and we try to concatenate them. Then we pass that into multi-layer perceptron. Then we have some sort of like a softmax to predict if like this is this posting is legal or illegal or something like that, right? So it's important to also note that not all of these features that we're passing through they're gonna have the same weight, because for instance the number of reports could be greater than the location. So it's important for us to apply weight on some of the features. So because we know that okay, this could be having more meaningful contribution to the model being accurate. However, um, also I pretty much like Uber design, whereby in their ETA they used a linear transformer for the token um, mixture. So by that, what I'm saying is that instead of having a dot product, we can have attention mechanism, because each feature is going to attend to another feature. So this way, you also get to build a very robust model. So, however, they used, like I said, they used a linear model because the attention mechanism is quadratic. So to avoid this, they use the linear model, which is I think O(n), right? So attention is quite good for having these features and combining them, like in order you can have like something very good. So, but however, because of this is not an NLP uh, what is it task. So what you do is that you remove things like positional embeddings, because you don't need the position, so to speak. So I want to say that there are different types of like a linear transformers. We could be having a performer. This was a model that was also introduced by Google. So here we try to approximate the attention matrix by making assumptions of sparsity or low rank, and we have a long former, I think. So with long former, it's also aimed at like the notion of having like some sort of like a global attention. I think this is also including the sparse transformer. So this is whereby this sparse transformer they also made assumption that not all only few tokens attend to other tokens, something like that, or maybe have a meaningful interactions. So they try to approximate sparsity. Another motivation for us that we can use to say that yes, it's fine for us to use like linear transformer for us to concatenate these features. I think Google, no, not Google, I think it was Facebook that is using also a linear transformer um, on their hate speech detection. I think they're calling it linformer. Um, so this is another model that they use, and I think it's based on the notion that we divide like matrices into multiples or smaller ones. Please check out my YouTube channel whereby I explain these and give like a high level overview of like what these models do behind and something like that. Um, but yeah, I think like I said, one thing that I want to say, guys, before we continue is that machine learning engineering is different from software engineering in such a way that yes, in software engineering we do have trade-off, like right, but most of the time the trade-offs are well known beforehand, so we can make decisions. But with machine learning engineering, we require experimentations. If sometimes yes, you can be quite confident that okay, this might work, but even that's the case, you still require to experiment because the data could be different, scenarios could differ, something like that. So that's one thing that I'll say. Okay. We can use a binary cross entropy as our loss function. So this is also known as a log loss. So it measures the distance between the predicted probability and the truth distribution. Um, so to capture how our model is doing, we can have a confusion matrix whereby we're assuming that the positive class is the illegal posting. And if this is the case, then we know that we want to minimize the false positive because we know that like if we don't minimize the false positive, like that means someone is going to sell the car and the company can be fined. So the expensive of like false positive is very high. So I'll say like let's take a hit on false negative. Why? It's because if we wrongly detect that okay, we say that okay, this posting was illegal and it was not, then we can handle that by the support team. Although that will not give a good a good experience. Some people might not like that, but for the most part, I think this one should be prioritized, right? But however, recall and precision they don't give like a high overview of like the model performance. So we can use like a model like F1 score, which is harmonic in a way that it try to capture how we are doing for both recall and precision, right? And for us to, because we thought that we want to minimize the false positive, we can use a model such as AUC, whereby we can be able to visualize and see the sensitivity and specificity. So we can think of here as like we try to max out the true positive rate, whereas we try to minimize the false positive rate. So here, the true positive rate, like I said, is that we're able to detect legal postings as illegal. So here we're doing well, right? But we don't want to predict like number of legal listings classified as illegal or something like that. So we try to minimize this portion. However, I have to say that this AUC does not capture like negative, false negative. So, and at some point you might want to do that, especially if you want to use a threshold to say that, okay, I want to max out the true positive rate. So another method that you can use is to use the recall and precision curve. So I think also it can help if you care about the false positive and false negative. So like I said, we're using the loss function log loss, so our model can be quite confident, and that could be quite bad for us in the production. So overconfident model can lead to a very catastrophic damage, right? So what we do is that we have this technique called confidence calibration. So we may not validate a legal listing as a result of our model being like overconfident. So that's the impact. However, what we can do is that we can minimize this. We can use the confidence calibration, right, to minimize the false positive and false negative by adjusting the model output probability to better match the um, true probability of the classes, right? So the confidence calibration help us to filter like poor predictions, whereby we try by all means to make sure that the probability, if the model assigned 90%, we know that that's correct, right? It's something like that. So there are different types of calibration techniques, like you can use Bayesian, which is quite expensive to train. You can use temperature scaling. We can use this in our deep learning model. We can use mix-up ensemble technique. So this one also requires you to train multiple models, so maybe it might not be efficient. But essentially, this is it, guys. So now we're gonna go into like the MLOPS pipeline, and we're gonna see how we can actually go about this. You still remember our first requirement was that we want to detect these users as they upload, so as soon as possible. But some of the users, like I said, can implicitly not let us know if like they're uploading an illegal posting. They can try to hide it somehow, right? So we're gonna leverage behavioral features. So because we have like, we wanna catch them fast, we can have a request respond architecture, and we can have a streaming architecture for the behavioral features. So that's what I'm gonna walk you through. So we can think of this part here as we have, I'm gonna start you from where we began. So we know we started with like saying that, okay, we're gonna have like data source, we're gonna have like features, then we have those feature processing steps to create our feature store, right? And like warehouse, we store like all that data inside here. And we talk about data scientist playground, and you can think of this as a data scientist playground. They retrieve the data, they do model training, evaluate, and then they load the best model inside the model registry. And all of the experiments are being tracked with a tool like MLflow, right? We're orchestrating all of the data scientist playground using an orchestration tool like Kubeflow, okay? So here, we can have a webhook to say that, okay, when the user select production, then that model is being deployed as a container, as a Docker container, and it goes inside this Kubernetes cluster. So the load balancer hit the gRPC, then the model retrieve the predictions. So we have an app. The user tried to upload, for instance, an image, and as the image hits the model retrieve the predictions in real time. So like immediately. So we're just leveraging the features here. From our feature store, we could be using something very fast like Redis to retrieve them, so that we can have low latency. So that's the design for stopping them as quickly as they upload. That's like a high level architecture for the MLOps. Now the problem becomes, what if, for instance, they upload, what if they don't tell us, like they upload their TV but they sell in drugs? What we can do is that this is where we're going to leverage, we're going to change our architecture a little bit to say that, okay, we're going to have some sort of like Kafka, right? Whereby all the real-time features, so the interaction, number of customers that bought for the last 30 minutes, who are the customers that are buying, how many products are they selling, when did they upload this. So the assumption here is that, right, how many people order from the listing, right? Will it make sense for us to have like 5,000 of orders in like less than 30 minutes? Will it make sense? No, it doesn't make sense. We've never seen something like this. So this is a suspicious behavior, right? So that's why here we're saying that, okay, as the feature comes in, as the people are buying, we have a Kubernetes cluster, but we also have some sort of like a Flink whereby we process all of these models. So it's like Flink application. Then after we process these model, we pass them through. After we process these features, we pass them through the model. Then we pass the results into the process features, and ready is consumed from this. Then the app, as the user makes a request, we check from the Redis the features, if like this user has been banned or anything like that. Right. So this part here, the above part is still the same. It's still the same. Nothing has changed. Data scientist playground, experimentation, and we have model registry, and we deploy our model as a container, including as a in a container with the Flink application. Right. The only thing that changes is that we just need to make sure that we track each and every event that is happening on application. User board, we track that. Somebody did this, we track that. Then we apply. We use our Flink to get feature store, right? It gets feature store features, right? And it gets real time features. It tried to concatenate them the way we did them in in the training. It passed them through a model. The model then process them and load the predictions into Redis. Then the user, as they try to interact, we try to check their status if they are blocked or not. Right? So that's like the behavioral part of things, and this is like the real time. Both of them are. This is like real time features, but there's maybe there might be a little bit of latency because now the user have to like do so those interactions. But those are the two architecture that we can go with. So things that we might consider, guys, is that we can do an A/B testing to check if like when the user upload, we're not like affecting their um their user experience. So there are certain things that I won't go deep into. I feel like there are certain things that are good for certain problems, like A/B testing. I think when you're talking about like something like clicks recommendation system, I'll have spoke about it in more strongly. I didn't talk about data model visioning, advisory attack, monitoring performance, model retraining, which is quite important, and logging of this. But these are like all the things that we could consider, right? So now let's look at the optimization. We made like some broad decisions, I think. Uh, so like we said, we're gonna use like deep learning for our deep NLP. So we can we can try to prune our model while we're still retaining like the same accuracy. For example, our the model that we can fine tune like ResNet 50, we can try to prune it. It has 26 million parameters. And we can take that to 5 million parameters while we're still maintaining the same accuracy. So we can use the technique whereby we train connection, we prune, train the weights, prune connection again, prune the connection. So just like that. But the reason train aware pruning is that we're still trying to maintain accuracy, right? Please check my YouTube channel whereby I go deeper into like each techniques like knowledge distillation, distributed training, all of these techniques like all about efficient deep learning. So check them out. For now, I'll just be touching them at the high level. We can also talk about knowledge distillation, whereby we train some sort of like a student to learn from a teacher. So we can apply things such as task agnostic knowledge distillation. So for instance, we can see that for example, like the still model, which has like 40% fewer parameters than the original bed. However, it's still quite expensive. I think it has something like 66 million parameters. So in the case whereby we have to like turn our text into like word numerical representation, I'll say like Wade is still quite a very good model that we can use. It's faster than bed. So like I said, like most of the time, machine learning is all about experimentation. We can also try to use models such as model bed, tiny bed, and to compare if like they still give us low latency, but they will just now concern more about accuracy, right? Like I said, we can probably use a linear transformer to get better predictions also. So in terms of neural architecture search, I think we can use something a tool like Raytune, whereby we apply things such as Bayesian optimization in a distributed fashion. If we're gonna do something like distributed training, which this is gonna allow us to distribute to search the parameters in a distributed fashion, right? So yeah, guys, I think this is the end of the machine learning system design. Yeah, I think as much as I go, I'll try to improve. Just give me feedback, then I'll improve in terms of like maybe how I communicate this information to you guys. If you feel like maybe you did like this, let me know, and yeah, I appreciate it. Thanks. Bye.